Hello everyone, my name is Hanrui Wang. I'm a second-year PhD student at MIT. I'm very glad to introduce our recent work on HAT, hardware-aware transformers for efficient natural language processing. Transformer models have been widely used in many NLP applications, such as machine translation and document summarization. Although achieving high performance, they are challenging to be deployed on resources-limited hardware devices due to the exponentially increasing model size and computation. For example, with the Transformer Big model, a Raspberry Pi needs to run 20 seconds to translate a 30-token sentence. The recent several models even cannot be fit into the GPU memory. To make things worse, it is also difficult to design an efficient transformer. Existing work, the evolved transformer leverages neural architecture search to search for a model. But the search process itself is very expensive, which produces 5 times of a car's carbon dioxide emission in its lifetime. This issue was discussed in a paper last year in ACL 2019, and this year we bring HAT as a solution to enable green AI for environmental friendly training and tiny AI for efficient inference. In HAT, we aim to design efficient transformer models with efficient architecture search. The transformer model efficiency is achieved by making the search process hardware aware with latency feedback inside a novel design space. The efficient search is achieved by conducting the architecture search inside a weight-sharing supernet called SuperTransformer. What makes hardware aware important? For the evaluation of transformer efficiency, we found 2 common pitfalls. The first one is that flops cannot reflect the real measure latency. In the figure, 2 models with the same flops but different layer numbers and hidden dimensions can have very different latencies. Second, latency is influenced by different factors on different hardware. As shown in the figure, hidden dimension is an influencing factor for Raspberry Pi, but does not have much influence on the GPU latency. Therefore, different hardware should have different strategies for efficient model design. To this end, the previous paradigm in which one general transformer is deployed on all hardware must be changed. In the HAT framework, a specialized transformer is designed with hardware feedback for each platform, so that we can get better efficiency than the general transformers. The HAT framework contains 3 main steps. Firstly, we train a transformer supernet named SuperTransformer with weight sharing. Secondly, an evolutionary search inside the SuperTransformer with a hardware latency constraint is performed to get a subtransformer. Finally, the search subtransformer is trained from scratch to get the final performance. For the SuperTransformer training, we construct a novel design space by breaking 2 conventional transformer design rules. The first one is that previously, all the decoder layers have to attend to the last encoder layer, which forms an information bottleneck. We propose arbitrary encoder-decoder attention to break the bottleneck and let each decoder layer attend to arbitrary and multiple encoder layers. Information from different abstraction levels are concatenated together and fed to the decoder layers. Another convention is that all the encoder or decoder layers have the same architecture. HAT breaks convention with heterogeneous layers to allow different layers to have different architecture adapting various hardware. The SuperTransformer contains all possible designs in the search space with weight sharing. It supports elastic embedding dimension. Subtransformers with different embedding sizes share the front part of the embedding vectors. It also supports elastic head number in self-attention and encoder-decoder cross-attention layers. Subtransformers with different head numbers share the query, key, and value vectors. HAT also supports elastic hidden dimension of the FFN layers. Subtransformers with different hidden dimensions share the front part of the weights. Besides, the layer number is also elastic. All subtransformers share the front several layers. As a recap, the encoder and decoder both have elastic embedding dimension, elastic attention head number, elastic hidden dimension, and elastic layer number. Arbitrary encoder-decoder attention is also supported. At each training step, we uniformly sample a subtransformer with a certain combination of design choices, get the gradients, and update the corresponding part of the weights. In this way, subtransformers with different architecture are equally trained and can operate independently. The trained supertransformer contains numerous subtransformers. Some of them may be preferred by IoT devices, and some of them might be preferred by GPU. We need to conduct hardware-aware search to find them. The function of the supertransformer is to provide a fast and accurate performance proxy. We can evaluate a subtransformer by inheriting that part of the weights from supertransformer and test the validation loss very fast, so that we do not need to train the subtransformers to the end. From the figure, we can see that the performance proxy is very accurate. The smaller the validation loss, the better the final performance. In the second step, we conduct an evolutionary search to find a good subtransformer. The evolutionary search engine aims to find a model which has low loss and satisfy a pre-specified latency constraint. The engine evaluates the validation loss of subtransformer architecture with weights inherited from supertransformer. It also gets the latency of subtransformers with a latency predictor. We use a latency predictor instead of measuring latencies on the fly because the predictor can provide much faster feedback. We first collect a dataset of pairs of subtransformer architecture and measure latency. Then we train a multilayer perceptron to regress the latency. The predicted latencies are very accurate and have root mean square error of only 0.1 second for Raspberry Pi. Finally, after several iterations of evolutionary search, we get a subtransformer and train it from scratch to get the final performance. We evaluate HAT on machine translation tasks. The figure here shows the latency and BLEU score trade-off curves of HAT and baseline transformer on WMT English to German task, running on Raspberry Pi. The yellow curve here is obtained by scaling the number of layers of the baseline transformer. The blue curve is got by dimension scaling of baseline transformer. HAT models are on the red curve. We can see that HAT achieves 3x faster and 3.7x smaller model size over the baseline transformer. On the NVIDIA GPU, HAT achieves 2.7x speed up. Note that simple dimension scaling cannot reduce latency of baseline transformer on GPU. On 3 other machine translation tasks, HAT also consistently outperforms baseline transformer on diverse hardware platforms. Here, we visualize 2 search subtransformers for ARM CPU and NVIDIA GPU. They both achieve 28.1 BLEU score, but have very different architectures. The GPU one has larger embedding dimension and smaller decoder layer number. From the 2 results, we found that the efficient model for GPU is not efficient for ARM CPU and vice versa. Therefore, specialized model for each hardware is necessary. Compared to the evolved transformer, HAT achieves 0.1 higher BLEU score with 2.7x speed up, 3.7x smaller model size, 3.2x fewer flops, and over 10,000x less search cost. On WMT English to German translation, HAT has over 12,000x smaller cost with the same accuracy. HAT is cost efficient because in the evolutionary search, it leverages the performance proxy from the supertransformer instead of training all subtransformers to the end. Compared with Levenstein transformer and Light transformer, HAT also has lowest latency and highest BLEU scores. More importantly, HAT is orthogonal to the new operations in Levenstein transformer and Light transformer. and HAT can be used to improve the efficiency of those models. In addition, HAT is also orthogonal to general model compression techniques. With 4-bit quantization, HAT can achieve 25x model size reduction with similar BLEU score. We have released the code and 50 pre-trained models for HAT on the GitHub. We also provide latency, BLEU score, model size, and flops of those models for easy comparisons. Please feel free to check it out and play with it. To sum up, we propose hardware-aware transformers to push the frontier of green AI and tiny AI. HAT searches for a specialized model for each hardware. In the design space, we introduce arbitrary encoder-decoder attention and heterogeneous layers to improve the performance. HAT achieves 3x speedup, 3.7x smaller model size, 12,000x less cost over the baselines. For more information, please visit our website at hat.mit.edu. Thank you very much for listening, and welcome to my live Q&A session on July 8th, 13 and 21 o'clock UTC.